What if the greatest engineers in history lived 1,000, even 1,000 years before us? Monuments carved straight into mountains with no trace of tools. Stones heavier than jumbo jets, stacked higher than modern cranes can reach. An ocean city built from volcanic columns and underground chambers that sing when you speak. They weren't supposed to be able to build these, and yet they did. The question is how? 30 meters underground, in chambers almost the size of football fields. There are stone walls marked with parallel grooves, meticulously cut over thousands of square meters. The caves have survived floods and earthquakes for centuries. Archaeologists say these structures could be over 2,000 years old, but lichen growth on nearby grottos suggests they might actually be from the Ming Dynasty. That's a staggering difference of 1,500 years. We'll explore why nailing down the date of the Longyu Caves is such a scientific and historical nightmare. Under a dim worklight, two archaeologists crouch in a shallow pit of fine, damp silt. Their gloved hands lift out small fragments, edges of bowls, the neck of a jar each piece, coated in the same sepale dust that has covered it for what could be centuries. The glaze still holds a faint sheen. Though the colors have dulled, the fragments have been lying in total darkness since they were left here, shielded from weather, light, and human touch. When specialists examined these ceramics, they recognized familiar features. The curve of the rims, the firing temperature evident in the clay, and the style of the decorative glazes matched items recorded from the Western Han Dynasty, a period spanning from 206 BCE to 23 CE. These were not random kitchenwares from a later era mimicking older styles. Their manufacturing traits tied them to a specific technological moment in Chinese pottery production. If these sherds were part of the original occupation or construction phase of the Longyu Chambers, it would place their creation over 2,000 years ago. But that connection carries an immediate challenge. Artifacts don't always remain where they start. An object can survive multiple generations, be moved, reused, or redeposited long after its manufacture, without evidence showing these pieces were sealed into the cave sediments during its earliest history. The argument for a Han-era construction remains uncertain. Dating pottery often relies on typology, the study of how styles and manufacturing techniques change over time. Archaeologists build chronological frameworks by comparing newly found pieces to items recovered from sites with secure timelines. When a ceramic form disappears from the archaeological record, it brackets the time in which it could have been in use. In this case, the Han-era diagnostic features give a narrow manufacturing window that offers a starting point. But typology only tells us when an object was made, not when it was placed in a specific location. The silt where the pottery lay isn't just background material, it's a record of deposition. The stratification, the layering of fine sediments, could tell whether the objects sank naturally over time, were buried during abandonment, or washed in from outside during a flood. Observers noted these ceramics were embedded within compacted silt rather than sitting loose on the cave floor. Still, without a clear, undisturbed layer sealing them in place, their association with the original carving stage is not conclusive. Another difficulty is the absence of other datable finds from primary contexts, locations directly linked to the construction process, like tool caches, working floors, or organic remains trapped during excavation of the sandstone. This silence in the material record means the dating depends heavily on a handful of objects, a risky basis for firm conclusions. If the caves truly were cut during the Western Han period, one would expect some trace in the written sources of the time. The Han dynasty left a rich corpus of chronicles, administrative records, and inscriptions on major infrastructure projects, yet no known document describes a project remotely like the excavation of 24 vast underground halls in this region. The omission raises questions about whether the pottery's presence reflects the original builders or a later cultural activity that left no surviving record. For now, those ceramic fragments remain the most tangible link between the Longyu caves and the deep past. They outline a possible origin date more than 2 millennia ago, a starting point from which timelines can be drawn and challenged. But not all lines of evidence point in the same direction. Just 200 kilometers away, another monumental cave complex has been examined with very different results. On a bare rock face, a thin crust of lichen spreads outward in slow, uneven circles. Each patch expands by only a millimeter or two a year, so slowly that its growth can be tracked over decades. In some parts of the world, scientists have used this steady pattern as a kind of clock, reading the maximum size of lichen colonies to estimate how long a surface has been exposed to the elements. It is not growth rings. On wood, they grow on stone, but the principle is similar, a record of time passed since the rock was first laid bare. This method, called lichenometry, was applied to the Huashan Grottos, a network of hand-carved chambers in eastern China that share notable similarities with Longyu at Huashan. Repeated measurements of lichen on key surfaces suggested that the rock had been exposed no earlier than the Ming dynasty, roughly in the 1500s or 1600s. That conclusion pushes their creation forward more than a millennium and a half beyond the possible Western Han date implied by the pottery at Longyu. If these two sites were built around the same time and by related traditions, the lichen results pose a sharp question. Is the Longyu network much younger than the ceramic fragments suggest? Or was Huashan itself a later project inspired by something far older? Lichenometry works by establishing a local growth rate. Researchers measure the diameter of the largest colonies on a surface and compare them against modern examples or historical surfaces with known exposure dates. With enough data, they can project backwards to estimate when the stone was first uncovered. The method is attractive in places where no organic remains survive for radiocarbon dating, and it allows dating of bare rock directly without relying on nearby material. However, the approach assumes that growth rates remain constant over long periods of time, and that lichen begin to grow soon after the surface is exposed. Environmental changes, microclimates, and rock chemistry can alter these rates. Some lichens grow only under direct sunlight, others in constant shade. One section of Huashan may have been moist and shaded, causing slower colonization, while another, exposed and dry, might have encouraged faster growth. At Huashan, the lichen data appeared consistent and supported the Ming-era exposure date. Some scholars note that certain architectural and stylistic elements, such as the arrangement of chambers and the groove patterns on walls, resemble those at Longyu. This stylistic overlap is part of what fuels comparisons between the two sites. Counter-arguments focus on differences in setting. Huashan's carvings are closer to open air, while Longyu's interiors are entirely enclosed once the entrance is sealed. Conditions affecting lichen growth at Huashan may not apply to the sandstone of Longyu, a surface cut in antiquity but kept dry and unlit could resist colonization, meaning lichen size there might reflect only a later period of exposure if the caves were opened or altered. This opens the idea of multi-phase construction. It is possible the Longyou Caves began as a Han period project, were abandoned or sealed, and then reopened and reshaped during the Ming Dynasty. New carving during this later phase could create fresh surfaces for lichen to colonize, leaving no growth record of the earlier work. Stone complicates dating because it rarely contains organic material that can be tested. Without wood, bone, or plant fibers trapped at the time of carving, radiocarbon techniques cannot be used. That forces reliance on indirect methods like lichenometry, comparative style, or associated artifacts, each with its own uncertainties. The lichen data from Huashan is a piece of evidence that cannot be dismissed. It points either to a much later origin for Longyou or to significant modifications in the Ming period that obscure the earlier history. That uncertainty shifts the discussion from when they were made to a broader puzzle: who created them, and for what purpose. If their true timeline refuses to settle, the Longyou Caves remain one of the few sites where physical evidence resists a single agreed date. Pottery fragments suggest a connection to the Han Dynasty, yet other methods point to a much later period. This conflict turns the site into a living question for archaeology, where each interpretation still lacks final proof. Consider how you would judge between an artifact's manufacturing date and scientific analysis of the stone itself. Share your reasoning, because both paths carry uncertainty. And if we cannot even be sure of the century these chambers were cut, what other histories might remain hidden in plain sight? Over 1200 years ago, a king ordered a temple worthy of the gods. Legends say it had to be ready in record time, carved from the living rock so it could never be destroyed. The artisans began at the mountain's summit, chipping downwards, revealing columns, elephants, and towers as if liberating them from stone. This was Kailasa, an audacious gamble in both design and engineering. But beyond its beauty lies a problem that still puzzles researchers today. How do you carve perfection on the first try? From a distance, the structure rises like any stone-built temple of its age, towers stacked with tier upon tier of carved forms, flanked by sculpted elephants and arranged around open courtyards. But there's no foundation trench, no separate masonry blocks, no join lines at all. Every column, every wall, and every carving is part of a single basalt outcrop that once formed a solid mass of the hill itself. What you see is what remained after enormous volumes of rock were cut away. The builders didn't create it piece by piece. They removed everything that wasn't the temple. That choice alone makes Kailasa stand apart, because it follows the floor plan and ornamentation you'd expect from a Dravidian-style temple, yet not one element is assembled. Instead, the entire plan was excavated downward into the mountain in a series of precise stages. What remains unexplained is how, in the 8th century, a project of this scale could be executed without even a surviving inscription detailing who laid out the work or in what sequence the teams progressed. Other temples leave foundation records or dedicatory notes about construction. Kailasa offers only royal dedications, not the slightest explanation of technique, and it stands as the largest known single rock-cut structure anywhere, dwarfing other examples where at least part of the construction involves separate stones. The core sanctuary stretches about 164 feet in length, 109 feet across, and rises around 98 feet from base to summit. These are dimensions on par with major freestanding temples of the period, but here the volume is defined in negative space, Each courtyard was hollowed out, each floor level open to light from top-down excavation. This meant the very first cuts at the highest point set the limits for everything beneath, a sequence that allowed no revisions. You couldn't add material back if proportions fell short or columns were misaligned. It's similar in principle to trying to build a detailed sandcastle by shaving the grains from the peak downward. Every accidental slip could damage finished work below. The strategy meant the temple emerged intact as the rock around it vanished, a process that demanded precise surveying from the very start. Historical parallels point toward models in existing freestanding temples, such as the Virupaksha temple at Pattadakal or older complexes in Kanchipuram. These show the architectural vocabulary Gopura gateways, pillared halls, circumambulatory paths that the Kailasa builders adapted here, but scaling these forms into a monolithic block required measurement and proportioning techniques we still don't see traceable in the quarry marks. Adding to the puzzle is the absence of any visible support holes or sockets for scaffolding across the upper tiers. How carvers maintained alignment of sculptures on opposite sides, separated by dozens of feet of void, is unknown. Stonecutters working simultaneously at different levels had to keep every surface matching the intended geometry without conflicting with other teams' work. What archaeologists have been able to confirm is that the top-down design was not arbitrary. Hollowing from the crown downward ensured the mass always supported itself, preventing catastrophic collapse that might occur if the base were removed first. This approach combined structural safety with aesthetic control, allowing the proportions to remain perfectly integrated from summit to base, a safeguard in the language of engineering. Applied centuries before, formalized structural analysis existed. And yet, even with the method understood in principle, one problem remains unresolved. For Kailasa to emerge, an immense quantity of stone had to be carved out and removed from the site entirely. The ground where we'd expect the spoil heaps to lie is bare, the surrounding slopes holding no sign of waste rock that would match the scale implied. Which raises the question, when that mountain of stone disappeared, where did it go? Hundreds of thousands of tons of hard basalt once filled the space where Kailasa Temple now stands. All of it was cut away, shifted from the site, and dispersed so completely that not one confirmed dump site has been identified. No mounds on the nearby plain, no hollowed-out quarry pits, no written record that says where the mass of rock went or how it was moved. It is as if the raw mountain was unmade, with only the temple left behind. Archaeologists working on the site over the past century have tried to calculate the missing volume. Most place it around 200,000 tons for the core excavation alone. Others, factoring in the surrounding courtyards, detached shrines, and approach passages, argue the figure could easily reach 400 tons or more. The numbers depend on how the calculations are done, whether the voids are measured directly in cubic feet, then converted to weight, or by estimating excavation rates from comparable projects. The results vary because not all surfaces are evenly cut, and later modifications in the centuries after the initial work may have added to the total removed. Even the smallest estimate represents a scale of labor that is difficult to relate to modern experience. Moving 2,000 tons of rock today, using standard 20-ton capacity trucks, would mean around 10,000 full loads driving away from the site. The full upper range would double that. The physical act of removing this mass without modern equipment meant an organized sequence of breaking it into smaller blocks, moving it downhill, and transporting it far enough away to avoid obscuring the temple grounds. Yet no trace of an organized spoil area survives. The most straightforward explanation offered is that the material was reused. The Rashtrakuta dynasty is known to have invested heavily in military works, so some suggest the stone may have been carted to nearby fortifications or settlement walls. Others believe the spoil was used for roadbeds, drainage channels, or secondary building projects now lost to erosion or later rebuilding. But no site in the region contains enough ancient basalt to match even a fraction of what Kailasa's excavation would have produced. Without archaeological layers that clearly date and match the temple's particular rock, these remain proposals without direct evidence. Because of this absence, more speculative possibilities have been raised. One is that detailed engineering records, now lost, might have described an entire removal network, teams tasked solely with shifting debris in a patterned system, dispersing it gradually so the change to the landscape never concentrated in one place. Another is that blocks of suitable shape were transported much farther for projects whose remains have not been identified or have been destroyed. Such ideas are hard to evaluate because no inscriptions, manifest lists, or references to massive stone shipments survive from that period in the Deccan. This puzzle isn't unique to Ellora. Other Indian rock-cut works, like the unfinished reliefs at Mahabalipuram or incomplete excavation chambers in various cave temples, also show volumes of stone removed without corresponding spoil piles. In each case, centuries of agricultural use, erosion, and human settlement have altered the landscape, making the original disposal sites almost impossible to detect without targeted surveys. The copperplate grants issued by Rashtrakuta rulers mention the temple only in terms of its dedication to Shiva and the legitimacy of the king's patronage. They contain no description of work crews, no timetable, no hints at the destination of quarried rock. This lack of documentation leaves the logistics of the project invisible, making the act of removal as mysterious as the precision of the carving itself. For researchers, that gap keeps Kailasa in the small group of historical constructions where even with modern scanning equipment, the full chain of operations, the extraction, the transport, the final dispersal has yet to be reconstructed. Laser mapping is being used to cross-reference the contours of surrounding areas with the temple's volume. But so far, no match has been found that could represent the vanished mountain. And this makes Kailasa less an isolated marvel and more a window into a wider, still hidden history of ancient scale, planning, and human ambition. Kailasa stands as a work of devotion shaped into stone. Yet it also remains an unanswered problem. Its form shows the skill of its makers, but the process that brought it into being has slipped from record. The very absence of that record turns the temple into a silent question for history. It invites a different view of ancient engineering, not as mystery born of legend, but as practical skill on a scale that is now difficult to reconstruct. Ellora holds more than this one monument, and each structure offers new gaps to explore, share, and keep in the conversation. Some of the stones in Sacsayhuaman's walls weigh more than 200 tons, yet were hauled uphill and placed with joints so tight they've survived centuries of earthquakes without mortar. The Inca achieved this without the wheel. Modern archaeologists can only theorize rope and lever systems, earthen ramps, something else entirely. What they all agree on is this: no one knows for sure. How can a wall built without a drop of mortar endure earthquakes that have reduced modern reinforced structures to rubble? On the hills above Cusco, lies a series of stone walls that face this question every day and continue to stand. The Inca built Sacsayhuaman with stones so large that the biggest are estimated to weigh over 200 tons. These blocks were shaped and placed more than 3,500 meters above sea level, forming part of a structure that dominates its ridge and watches over the city below. The site stretches in 3 great terraces, one above the other, so wide that the lowest wall is more than 400 meters long. Standing at its base, individual stones rise higher than a person's height. Look closely, and you'll notice that they aren't cut into neat, uniform blocks. Instead, their sides are chiseled into a variety of shapes and angles, each one matching its neighbors like part of a giant, irregular puzzle. Between them, there's no mortar. No filler, just contact edges so tight that a modern sheet of paper cannot pass between them. This level of fit was achieved without the use of steel chisels, wheeled carts, or animals that could pull large loads. Each block had to be quarried, moved, and then positioned using only what human power, simple tools, and ingenuity could provide. Yet every joint is exact. Every surface rests perfectly in its place. Engineers have pointed out that the walls even lean inward slightly, giving them more stability. Each stone's unusual polygonal shape means that any movement is absorbed across many faces instead of just one, making the wall resistant to displacement. The zigzag formation of the main terrace is not just a striking design choice, it has a structural function, breaking up the force of seismic waves so that energy does not run through the wall in a straight line. This helps explain how Sacsayhuaman withstood historic earthquakes that leveled much of colonial Cusco. When Spanish chroniclers first saw it, they wrote of their disbelief that such work could be made by human hands. Garcilaso de la Vega, born in Cusco to an Inca noblewoman and a Spanish father, described how even small stones were adjusted with care so that no joint line aligned directly with another, spreading the pressure and locking each block into the whole. Modern explanations remain incomplete. Some scholars suggest the Incas used thick ropes, wooden levers, and coordinated labor teams to shift the stones over prepared paths. Others picture long earthen ramps, built up over weeks or months, allowing stones to be dragged gradually into position. These ideas have been tested on smaller scales, and they sometimes succeed in moving moderate-sized blocks. But no experiment has yet been able to replicate the exact shaping, positioning, and tight joints for stones of the enormous size seen here, especially on steep, uneven ground. Across decades of research, archaeologists, engineers, and experimental builders have returned to the same conclusion. While we can outline possible techniques, there is no single proven method that explains every feature. The walls have endured their environment not just by luck, but through a combination of interlocking geometry, careful shaping, and strategic placement that continues to challenge our understanding. And yet, the question lingers: what kind of society would invest the immense effort, time, and skill to construct such a fortress on this scale? To answer that, we have to consider its purpose. And that takes us deeper into a story that is even more complex than the walls visible on the surface. What if the mystery of Sacsayhuaman extends underground into a hidden network few have ever seen? Local tradition speaks of the Chincanas' stone-lined passageways said to reach from the fortress into the heart of Cusco, connecting temples, plazas, and sacred landmarks. For generations, these tunnels were spoken of in stories, sometimes with warnings. Accounts describe travelers who entered and never returned. or openings that were sealed by authorities for safety. Many historians regarded these tales as embellishment, reinforced by the lack of verifiable maps or accessible openings. That skepticism began to change when modern imaging tools were brought to Cusco's historic core. Ground-penetrating radar scans, combined with acoustic tomography mapping sound waves underground, revealed unexpected voids beneath certain sectors of the city. These empty spaces did not resemble natural caves. The contours suggested deliberate shaping, with narrow, tapering walls that formed a trapezoidal cross-section. That shape is identical to the Inca doorway and wall profiles still seen in surviving architecture above ground. The findings were significant because a trapezoid niche or corridor underground indicates intentional construction. It also reflects the same engineering decisions used in earthquake-resistant walls. On the surface, a narrowing at the top provides stability under shifting loads. Some of these voids appear to run in linear alignments, stretching from the direction of Sacsayhuaman toward the former location of the Coricancha, the Temple of the Sun. Measurements suggest certain segments are separated by considerable distances, implying either long, continuous tunnels or a series of connected chambers. Researchers have proposed several uses for such a network. One idea is ceremonial. The tunnels could have allowed processions to move between sacred sites out of public view, perhaps as part of specific rituals. Another is strategic, providing hidden routes between the fortress and city center would have offered a secure line of movement during conflict. A more symbolic interpretation links the underground routes to the Inca worldview, where the physical landscape mirrored a cosmic order, and pathways might mimic the lines and connections between Huaca spiritual landmarks linked by ritual pathways known as seques. Concrete examples from the scans show apparent connections between points beneath Sacsayhuaman's lower terraces and surveyed locations under what was once the Coricancha. Separate voids appear aligned toward other sites recognized as huacas around Cusco's periphery. None of these potential passageways are currently open for general inspection. Soil bore samples taken in the vicinity have pulled up worked stone fragments and compacted surfaces consistent with flooring, adding physical weight to the imaging results. Permits have been approved for more detailed investigation starting in 2025. These controlled excavations will target specific anomalies identified in the mapping data, using minimal disturbance to maintain the integrity of the overlying structures. Whether the work will uncover intact tunnel sections or only remnants is unknown. But either outcome will expand the record of how Inca Cusco was organized both above and below ground. Preserving these features presents its own challenges. Underground spaces can destabilize if opened without reinforcement, and tunneling in a city layered with centuries of architecture risks damaging later structures. Cultural protections require that any exploration balance research goals with the responsibility to maintain the site's heritage. For now, most Chincana entrances remain sealed, watched over more for their preservation than public access. These clues recast Sacsayhuaman as more than a defensive citadel. Its walls may mark only one part of a much larger network, an integrated system of sacred and practical roots binding the Inca capital together. If the Incas engineered such complexity above and below the ground, each to the same standard of precision, it forces us to ask how they achieved a harmony of design that has survived for centuries in two very different worlds. After centuries of examination, Sacsayhuaman remains a structure that resists full explanation above ground. Its vast walls display precision and resilience that challenge accepted limits of pre-industrial engineering. Below ground, Indications of constructed tunnels suggest an equally deliberate world hidden from view. Modern experiments still cannot match these achievements with the same scale and accuracy. If current tools and resources cannot reproduce the results, it raises questions about the knowledge and methods behind them. The answers, when found, may not simply fill a gap in history, they could alter the foundations of how we understand the capabilities of the Inca. How do you place an 800-ton stone 6 meters above the ground? 1,000 years ago, at Baalbek in Lebanon, 3 megaliths, each longer than a school bus, sit perfectly fitted atop an ancient platform. Even the largest modern cranes would strain to move them. Yet the Romans didn't have steel cables or diesel engines. In the next few minutes, we'll investigate the quarry 800 meters away. The theories about moving these giants, and why, despite everything we know about ancient engineering, no one can fully explain how it was done. Each of the 3 trilithon stones weighs more than 800 tons. Heavier than a fully loaded Boeing 747 on the runway, they are not lying on the ground. They rest in a single row, forming the highest course of the western wall of the Temple of Jupiter's immense stone platform. That platform sits roughly 6 meters above the surrounding terrain, meaning these blocks had to be raised to a height comparable to a 2-story building before being set in place. Baalbek lies in the Bekaa Valley of eastern Lebanon, on a site occupied for thousands of years before Roman times. By the 1st century AD, the Romans began constructing one of the largest temple complexes in their empire here. The 3 trilithon stones form part of the core retaining wall on the temple's western side, above several courses of smaller, though still massive, foundation blocks. The paradox becomes clear when looking at Roman lifting technology. Roman engineers created the treadwheel crane, the polyspastos, which used human or animal-powered winches and pulley systems. These could raise stones weighing in the range of 50 to 100 tons. The most advanced recorded rigs could reach about 300 tons under ideal circumstances. The trilithon stones are nearly triple this maximum figure, making them far heavier than any surviving evidence of Roman cranes could handle. Lifting such weights would have required machines or methods beyond what is documented from Roman construction sites. The dimensions of the trilithon stones are also notable. Each measures close to 19 meters in length, about 4 to 3 meters in height, and around 3-6 meters deep. They fit so closely together that the gaps between them are barely perceptible. Despite the immense size and weight, the upper surfaces are level, the front faces align smoothly, and there are no visible signs of reshaping after placement, suggesting they were set in position with precision rather than adjusted later. For comparison, some of the largest modern mobile cranes can lift around 1,200 tons under optimal conditions, but that figure is only achievable under controlled conditions on stable ground. With heavy counterweights and by lifting much smaller, more compact loads, long stone blocks of the trilithon size would be far more awkward to handle, with bending stress and balance complicating the process. The Romans not only would have lacked such large cranes, but also the steel cables, hydraulic systems, and engineered rigging that modern crews rely on. None of this means the Romans were crude builders. On the contrary, they created enduring works of architecture, aqueducts that carried water for many kilometers across valleys, amphitheaters that held tens of thousands, vaulted roofs, and monumental arches. They understood advanced mechanics, concrete, and the use of cranes in large-scale building projects, but all their known methods have clear limits, and the trilithon stones surpass them by a wide margin. This raises the immediate question: if a crane could not lift them, how were they moved into their current positions? Even assuming they were somehow levered or ramped up to height, maneuvering an 800-ton block with that degree of accuracy over other stone courses would be extremely difficult. The archaeological record offers no surviving devices or clear construction marks to explain the process. By every measure of known technology, raising and positioning the trilithon stones as they exist today should have been impossible. Yet they remain in place, solid and unmoved for nearly 2,000 years. And the puzzle becomes even more pronounced once we consider that these blocks were not shaped on the spot, they were cut somewhere else and brought here before ever being lifted. The trilithon stones were not carved where they now stand. They came from a limestone quarry known as Hajar el-Hibla, lying just under a kilometer from the Temple of Jupiter. This site still holds one of antiquity's best-known megaliths, the Stone of the Pregnant Woman, a partially cut block similar in size to the trilithon stones and still joined to the bedrock. Whether it was abandoned for flaws or left in place for other reasons is uncertain, but it makes clear that the source of the trilithon was within direct reach of the builders, even at that close distance. Moving an 800-ton stone on uneven ground without modern machinery poses a task as severe as lifting it. The Bekaa Valley's earth is a mix of compacted soil, loose gravel, and rock. In the 1st century, there were no paved roads leading from the quarry to the platform. Dragging such a load risks the stone sinking, cracking, or becoming impossible to shift when momentum is lost. The physical space to maneuver a block over 19 meters long without blocking or destabilizing it would be difficult to prepare over that terrain. Excavations at Hajar el-Hibla in 2014 revealed an even larger block, buried beside the Stone of the Pregnant Woman. This stone measures more than 19.5 meters in length, 6 meters in width, and 5.5 meters in height, with an estimated weight of about 1,650 tons, roughly twice the weight of any trilithon stone. It remains in situ, never extracted, perhaps because moving such mass would have exceeded any capacity, ancient or modern. For perspective, the largest wheeled transporters available today can move loads in this range, but only under tightly controlled industrial conditions with reinforced ground under their roots. Several practical theories have been proposed for how the original trilithon stones might have been transported that short but demanding distance. One involves building wide, compacted earthen ramps between quarry and construction site. While this could, in theory, provide a continuous path, the volume of material to prepare a stable ramp for hundreds of tons would have been enormous, and it would need to remain perfectly level to prevent shifting the load. Wooden rollers are another suggestion. Yet the weight of each stone would crush timber unless it was of exceptional strength and continuously replaced as the stone advanced. A variant of sled transport using lubrication water, clay, or animal fat could reduce friction and allow dragging across planks or stone. However, this method demands constant resupply of the lubricant and precise coordination to keep the block aligned. Multi-capstan systems, where several human or animal-powered winches pull ropes attached to the stone, could develop great pulling force, but the risk of uneven pull causing tilting or jamming increases with the block's size. Manpower calculations show one experimental approach required 512 workers to move a 557-ton load on rollers over level ground. Scaling that up to the trilithon's weight would push human and material limits, especially over varied terrain and without damaging the block. Adding to the curiosity, there are subterranean passages beneath parts of the temple platform. Some researchers suggest these may have been used to support or adjust blocks during placement, though no direct evidence ties them to the movement of the trilithon itself. Yet after considering ramps, rollers, sleds, and teams of hundreds, none of these solutions fully explains how the stones reached their final position without breakage or misalignment. The difficulty lies not only in imagining the tools and labor, but in the sheer scope of the project, a scale that suggests the builders of Baalbek aimed at something far beyond typical Roman construction. The trilithon stones stand as immovable evidence that ancient builders achieved results that modern methods still struggle to match. Their creation, transport, and placement remain without a complete, proven explanation. Even with centuries of study, this is not just a question of skill, but of ambition why such immense blocks were chosen at all. If work of this scale was possible 2,000 years ago, it forces us to ask what other feats have been underestimated or overlooked. Many ancient structures remain only partly understood, suggesting that the story of human engineering is far from complete and may still hold surprises. They say the past is a foreign country, but in Nan Madol, it feels like a completely different world. Here, there are no roads, no fertile farmland, no fresh water, yet for centuries it was the center of political and ceremonial life for an entire island. How did a city survive in such a place? And why did its rulers choose to build it there? The answers lie between archaeology and oral tradition, and they might just change the way you think about human ingenuity. According to stories still told on Pohnpei, the city was not built by ordinary men at all, but by twin brothers who had the power to command stones. In these accounts, the brothers, Olusopa and Olisipa, were sorcerers who could make the massive basalt columns rise into the air and float across the water as if weightless. The image is striking dark pillars hovering above the waves, settling into perfect formations without a single rope or scaffold. These stories are not preserved in dusty books. They are passed aloud, sung in chants, and embedded in rituals that link the people of today to the builders they imagine from the past. Modern media has seized on these tales. Travel guides recount them to set an air of wonder for visitors, while popular television shows present the idea as a possible sign of lost technologies or non-human intervention. A well-known series devoted to ancient mysteries once illustrated the scene with computer graphics of stones arcing across the sky, casting long shadows over the lagoon before landing to build the city. The narrative is compelling, easy to remember, and it thrives because no one can point to any written record that confirms or disproves such events. That uncertainty leaves room for a question that lingers if nothing was written down. Could the old accounts carry an element of truth, even if greatly exaggerated? When people hear about stones that could fly, their minds often go first to fantasy. But when they see the stonework in person, the scale forces them to reconsider. The city's walls are built from polygonal basalt logs, each often several meters long. Some columns approach 50 tons in weight, and structures rise more than 7 meters above the waterline. Figures like these make it easier to see why fantastic explanations survive. Without cranes, without wheeled vehicles, and without metal tools for shaping or cutting, the problem is as clear now as it must have been for any observer centuries ago. How can such immovable objects be brought here and stacked with precision? In this gap between problem and solution, speculation thrives. Some television segments even multiply the city's estimated total stone mass several times beyond credible measure, making its creation seem impossible without magical or extraterrestrial aid. The real totals are immense enough without inflation, yet exaggeration deepens the mystery for audiences drawn to the idea of an unsolved puzzle. But archaeology does not leave the question unaddressed. Dating techniques show that the construction took place over centuries, not in one miraculous burst. Geochemical analysis links the basalt to sources on nearby islands, matching the signature of columns still visible at ancient quarries. Excavations at these sites have revealed clear signs of systematic extraction. All of this points to human transport methods. Stones moved first over land to shore points, then across the water on rafts or canoes designed to bear tremendous weight. These methods demand extraordinary organization and physical effort, but they remain within human capacity. The picture that emerges is of sustained, coordinated labor by generations of workers, not supernatural beings. Every stone at Nan Madol is a testament to that effort, and while no sorcery carried them into place, the logistics behind their movement rival any tale of airborne construction in sheer audacity. This evidence settles one mystery, but opens another. If thousands of tons of stone could be moved from quarry to reef edge, how did the builders handle the final challenge, assembling and securing a city in the middle of the sea without local resources or overland routes to rely on? Nan Madol's location makes its existence even harder to explain. It stands on a shallow reef, cut through by tidal channels, with no natural source of fresh water and no space for farming. Any long-term settlement here meant depending entirely on supplies from outside. Yet the site was more than just occupied. It was purpose-built into a formal layout. The western section, Madol Pa, served as the seat of administration. The eastern section, Madol Pao, contained some of the most important ceremonial spaces, including burial compounds for the island's rulers. Both stood on artificial islets, separated by canals wide enough for small canoes to pass between them. Constructing a city on a reef meant starting from nothing. Builders needed a stable base, so they filled the foundation layer with coral rubble, a material light enough to transport by canoe but solid enough to spread on the reef floor. On top of this, they placed the heavy basalt columns brought from shore. Each platform had to be high enough to remain above high tide, which meant moving staggering amounts of stone just to reach a level surface before any walls rose. The basalt columns came from quarries on nearby islands. Workers shaped and extracted the pieces, sometimes in uniform lengths and sometimes irregular but close-fitting, before loading them onto large rafts or lashed canoes for transport across the lagoon. The journey had to be timed with tides and weather, since strong currents could easily push the heavy cargo off course or damage the vessels. Given the lack of metal tools, the cutting and fitting process was slow, relying on controlled fracturing of the natural basalt columns rather than carving from a solid block. Once stones reached the construction site, the risk of collapse became a constant concern. Builders had to stack columns several meters high on a base that was not solid ground but compacted coral. To manage this, they used what can be called a header stretcher arrangement, placing some columns lengthwise across the wall's width as binders while others ran parallel to the wall face. This interlocked the pieces, added stability, and allowed gaps between them to be packed with smaller rubble and coral fill. The method reduced outward pressure and spread the weight more evenly across the foundation. Modern estimates put the total mass of stone used at around 750 metric tons, Already an enormous figure, popular accounts often inflate this heavily, making the project sound physically impossible without supernatural help. In reality, keeping to accurate numbers does not weaken the achievement, it makes it more tangible. Showing exactly what human effort and organization have done, recent LiDAR surveys have identified more than 90 islets spread over roughly 18 square kilometers, some overgrown and obscured until mapping revealed their shapes. Many appear to have served specific functions within the city's network, from living quarters to storage to defensive positions. This scale was no accident. It reflected deliberate planning by the Sodelur dynasty, which ruled the island for centuries. Maintaining a population in such an environment required uninterrupted maritime supply lines, food, fresh water, building materials, and even firewood had to be brought in regularly. Coordinating this over centuries points to a high level of political control and logistical skill. Without constant attention, the structures face damage from storms, wave action, and the gradual weakening of coral foundations, a vulnerability that continues today. It's here, in the scale and precision of that long-term human effort, that the real fascination lies. Seeing Nan Madol as the product of coordinated labor, rather than supernatural force, opens a different kind of story, one where organization and human decision-making become the most remarkable parts of its creation. Moving hundreds of thousands of tons of basalt without cranes or wheels required quarrying, shaping, transporting, and stacking each piece with precision. It was an achievement of planning, manpower, and sustained effort over generations. The stories of flying stones may not record literal events, but they capture the sense of awe such work inspired. Seeing the city this way makes the human accomplishment no less impressive. If Nan Madol could be built in such a hostile setting, using only the tools and resources of its time, it raises a larger question: what other ancient feats could be explained in the same way? At 12,800 feet, above sea level, in the thin air of the Bolivian's Altiplano, lies a stone platform whose precision has baffled experts for decades. Each H-shaped block fits so perfectly, a razor blade can't slip between them. They weigh over 100 tons and were hauled from quarries miles away without wheels or modern tools. How did an ancient civilization pull off such a feat? The answer might change the way we think about human history, and it's hidden in the stones of Puma Punku. How can rock, harder than steel, be carved into shapes so precise they look as if they came from a factory floor? At Puma Punku, dozens of massive H-shaped blocks fit together with a smoothness that leaves no gap wider than a fingernail. The right angles remain sharp, not worn or irregular, and the alignment from block to block stays consistent for meters at a time. These measurements are not the result of erosion or chance, they are built into the original design. What makes it more puzzling is the material itself. Many of these blocks are carved from andesite, a volcanic rock with a Mohs hardness of about 7, close to that of quartz. This makes it far more resistant to shaping than softer building stones like limestone or sandstone. Red sandstone was also used in the complex, but it is the andesite pieces, the most intricate and exact, that seem inconsistent with the known toolkit of the builders. In the timeline when Puma Punku was constructed, there were no steel chisels, there were no diamond saws or high-speed abrasive wheels. The common tools of the region were hammerstones of even harder rock, along with techniques of abrasion using sand. According to standard archaeological interpretation, the shaping could have been achieved by striking the stone with hammerstones to get close to the desired form, then grinding and polishing the surfaces over long periods. It would have required precise measurement and repeated checking of angles during the work. Even so, certain cuts, perfectly straight interior channels, and uniform recessed planes show no obvious hammer marks, leading some researchers to note that the final finish remains unexplained by surviving evidence alone. It helps to think of each block as part of a vast, three-dimensional puzzle. The H shapes, along with other angular forms, were not decorative flourishes, they were functional components that locked together in a specific geometry. If one piece was even slightly irregular, the entire sequence of stonework would fail to align. Today, a skilled mason with a portable grinder could spend hours getting a single joint that precise. Here, hundreds of these connections exist, many repeated at the same size and depth. Adding to the complexity, the Tiwanaku builders used metal fittings to secure some of the blocks. Archaeological work has found evidence of cramps, metal connectors inserted into carved recesses between stones. Analysis shows these were made from an alloy of copper with arsenic and nickel, materials that require careful smelting control to produce. The cramps were cast to fit exact cavities, which means the masons and metalworkers had to work in coordination from the outset. The quarrying stages also tell a story of planning. Many of the sandstone blocks, though large, came from about 10 kilometers away. The andesite blocks were sourced some 90 kilometers from the site, across the shores of Lake Titicaca, yet the stones do not appear to have been brought roughly shaped and then finished on site. In many cases, the intricate details were already in place when they arrived, suggesting either a distributed workshop system or a logistical process capable of moving finished pieces over significant distances without damage. When seen in this light, the achievement is not just about beautiful stonework, it represents near-industrial control over measurement, material properties, and assembly. The people of Tiwanaku, working with nothing beyond stone tools, measurement systems, and coordination, produced results that rival the tolerances of modern engineered stonework. But there is still the question that hangs over it all. Once shaped, how did these immense stones, some weighing more than a fully loaded railcar, make the journey to Pumapunku in the first place? Imagine moving a block that weighs 131 tons across nearly 90 kilometers of varied, mountainous terrain. There are no cranes, no trucks, no paved roads. In the high plateau of the Andes, such a task would already be difficult today. For the Tiwanaku builders, it had to be done with what they could carry and make themselves. The sandstone blocks in Pumapunku came from a quarry about 10 kilometers away. That distance is still a major challenge when a single block can weigh dozens of tons. The andesite blocks, however, were quarried far to the south, in the Copacabana Peninsula region, across the waters of Lake Titicaca. This was roughly 90 kilometers from the site, much of it through rugged country. Some routes may have crossed parts of the lake itself, which would have required additional transport systems for such massive pieces. On the Altiplano, the air is thin at 2,800 feet above sea level. The reduced oxygen slows physical work, makes heavy labor strain the body sooner, and limits the strength and endurance of workers. The landscape is not flat. Despite being a plateau, slopes rise toward the mountains, and routes can include sharp inclines and coarse ground. Beyond the environmental challenge, there were no large draft animals suited for pulling such loads. Llamas were the largest domesticated beasts available, but they can carry at most about 40 kilograms each, useless for directly hauling multi-ton stones. The standard model from archaeology suggests that workers used thick ropes braided from llama hides, teams of people pulling on multiple lines, and sledges constructed from wood to spread the weight. The sledges could have been dragged over prepared paths lined with logs or stone rollers, or along earth ramps. For lake transport, reed boats, possibly large catamaran-like constructions made from bundles of totora reeds, are sometimes proposed as a way to move the stones along shorelines before continuing overland. Calculations for such a move can help put the effort into perspective. To shift a 131-ton stone, even on a well-prepared sledge, might require hundreds of workers pulling in coordination. The ropes themselves would have to withstand enormous tension, possibly in the range of tens of tons. Experimental archaeology shows that natural fiber ropes can handle impressive loads, but they also fray and stretch, requiring repair or replacement mid-task. The difficulties have led to ongoing debate. Some researchers propose that the builders used advanced leverage systems, frames and weights arranged to lift or ease stones, along with less brute force. Others see evidence that sections of Puma Punku display incomplete work, possibly due to the immense strain of moving the largest stones. In that scenario, the site's ambitious design outpaced the means to execute it fully. Outside the mainstream, alternative theories have developed. One is that the blocks were not quarried and carved in the traditional sense, but cast from reconstituted stone using some form of geopolymer process. Under this idea, builders could mold the stones in place without moving them over long distances. The counterpoint is that close geological study shows the stones retain their natural volcanic and sedimentary structures, with no sign of being artificial aggregates. Radiocarbon analysis of organic remains at the site places its earliest monumental construction between AD 536 and 600. Matching the growth of Tiwanaku as a regional power, it is not a relic from an unknown lost civilization, but a product of a society we know by name. In modern tests, teams of researchers have tried to move stones only a fraction of the size of the largest at Puma Punku. Even with better ropes and controlled conditions, the pace is slow, the force required exhausting. Scaling that up to blocks weighing over 100 tons offers a clear sense of the organization and planning the Tiwanaku must have commanded, both in shaping the stones and in getting them to the sacred platform in the first place. Puma Punku's precision and the sheer distances its stones traveled may seem beyond human ability. Yet the evidence shows a mastery of tools, planning, and coordination within the reach of the Tiwanaku people. They achieved what looks impossible without any hint of supernatural intervention. If stones this exact and movements this complex were possible with hammerstones, ropes, and organized labor, it raises a question: how much are our assumptions about human limits shaped by modern dependence on machines? Puma Punku stands as a work of skill and determination, reminding us to keep searching for what human ingenuity can still accomplish. In 1902, a stonemason in Paola, Malta, cracked open the roof of what he thought was solid rock and stumbled upon an underground world no one had seen for thousands of years. Passages twisted into darkness, red ochre spires danced in dim light, and in one chamber, a single voice could set the walls humming. That accidental break in the stone opened the door to one of archaeology's deepest mysteries. Why would a prehistoric people carve a hidden, three-level complex with acoustics modern engineers still can't replicate? How can a 5,000-year-old chamber control a human voice in ways that even the best-equipped modern concert halls struggle to match. The room in question is known today as the Oracle Room, an unadorned space cut into solid limestone. Deep within the hypogeum, it is small enough to feel intimate, yet its voice can stretch far beyond its walls. A single syllable spoken inside will not only linger, it will travel, resonating through the floors above and below, as if the rock itself had become a living amplifier. Researchers have mapped every angle, curve, and surface of this chamber. They know the density of the limestone and the approximate methods used to cut it. And yet, when they try to reproduce the effect in a laboratory setting, they fall short. Even precise reconstructions of its dimensions fail to capture the way sound swells and carries through the hypogeum. Something about this space works with the voice in a way that remains outside the reach of exact duplication. Measurements taken inside capture a distinctive acoustic fingerprint. The chamber resonates most strongly at around 110 Hz a pitch, roughly equivalent to the low A on a bass guitar. It also supports dual tones in the range of 70 and 114 Hz, which sit in the register of deep male voices and the lowest pipes of a church organ. To the ear, these notes carry a weight that is felt as much as heard. A voice within this range can seem to roll through the building's stone corridors, touching spaces the speaker cannot even see. Those who first documented the effect described a peculiar sensation as they spoke. Their chests vibrated in time with their words. The sound that came back was not an echo in the usual sense. It arrived fuller, almost layered, as if voices from some other source were speaking alongside them. If you could visualize it, the sound waves would not simply bounce. They would pour outward, rippling against the stone until the whole structure seemed to hum. The science devoted to studying these phenomena is called archaeoacoustics. In the hypogeum's case, it involves placing calibrated microphones and speakers in various parts of the underground complex, then generating sounds at controlled frequencies. Researchers map how the sound changes from one location to another, noting where it grows louder, softer, or acquires a different tonal quality. Vocal tests are also performed, using trained speakers to produce sustained tones while instruments record the chamber's response. These resonant pitches fall in a range known to overlap with certain human brainwave rhythms. When exposed to sustained low frequencies, the brain can shift activity patterns, a phenomenon that, in some settings, has been linked to altered mood, heightened focus, or trance-like states, whether intended or not. The Oracle Room's natural tuning places it within this potentially influential range. It raises the question, was this acoustic profile shaped on purpose, or did it happen by chance? The tools available at the time suggest trial carving and natural shaping as possibilities. But the precision of the effect makes some suspect intentional design. Complex societies elsewhere have famously engineered sound effects into monuments, so the idea is not impossible. In fact, when laboratory EEG tests exposed participants to similar frequencies, researchers observed measurable changes in brainwave patterns, reinforcing the idea that environments like this could influence human perception during vocal rituals. If understanding the hypogeum's sound was only a matter of physics, the puzzle might have been solved by now. But the clues suggest a layered purpose, one that may have combined architecture, sound, and belief into a single experience. To see why these effects could have carried such weight, it's necessary to move beyond the mechanics of sound and into the realm of meaning that the builders may have attached to it. A narrow corridor leads forward, lit only by the muted glow of torches. The air feels still, the passage low. Each step brings you deeper, until the stone opens into a space archaeologists call the Holy of Holies. It sits at the center of the Hypogeum's middle level. Here, the rock walls hold curved and geometric carvings. Painted patterns once wound across their surface spirals, lattices, and shapes that echo natural forms like honeycombs in the dim light. These designs catch the eye and draw attention to certain walls and openings. This level forms the largest and most complex part of the structure. The chambers are proportioned in a way that gives each its own character, some broad and oval, others narrow with high ceilings that seem to rise beyond the torchlight. The arrangement is not random. Some rooms are aligned so that an entrance frames another interior feature, while others lead directly to closed spaces. These patterns suggest planning that goes beyond the needs of a simple burial area. The idea of the Hypogeum as only a crypt sits uneasily next to what is found here. Decoration is rare in most prehistoric tombs, yet here it is present in multiple rooms. The careful shaping of apertures to mimic architectural forms found above ground hints at symbolic intent. Trilithon doorways, the same two-post and lintel design used in Malta's surface temples, stand carved into the stone. Corbelled ceilings reproduce the stepped effect seen in those same temples. Even though here there is no need for roofing against weather, these repeated motifs signal a deliberate connection between the above-world spaces of the living and the hidden spaces below. Among the thousands of human remains recovered from the middle level, archaeologists found the small limestone sculpture known as the Sleeping Lady. The figure is depicted lying on her side on a platform, wrapped in what might be a blanket or garment. Her rounded form and closed eyes suggest rest or death, and some propose she represents a goddess or guardian, closely tied to the fate of those buried in the chamber. The bones themselves tell a story of long and repeated use over centuries. Many are marked with traces of red ochre. This pigment, drawn from iron-rich earth, has been used in many ancient cultures to symbolize blood or the renewal of life. Placing it with the dead may have been part of a rite intended to guide or transform the spirit. Sound may have played a key role in these events. The same acoustic qualities measured in the oracle room above would have resonated through this level as well. A chant timed to its frequencies, produced by a speaker in a neighboring chamber, could vibrate the air and body alike. A beat from a skin drum, low and regular, could carry along the same paths, reaching every space carved into the limestone. In such conditions, light is scarce and vision limited to what the lamps reveal. The long absence of daylight distorts time, while the confined space amplifies each breath, shuffle, and word. Combined with sustained sound in the resonant range, the underground experience could shift a participant's perception, making the ritual both a sensory and a psychological event. Seen together, the layout, art, and acoustics appear interlocked, forming a system that works on the body and mind at once. The Hypogeum may not have been a place to only store the dead. It may have been designed to change the state of those who entered. Today, only a small number of visitors are admitted at any time. To prevent changes in humidity and temperature from damaging these conditions that have lasted so long, the Hypogeum brings together precise construction, symbolic spaces, and an acoustic effect that resists full explanation. Its architecture serves both practical and ceremonial purposes, yet its strongest impact may still be the experience it creates for those inside. Whether the resonance was an accidental outcome of excavation or a carefully engineered feature, It operates in harmony with the rituals suggested by its art and layout. In this way, it preserves a kind of knowledge that does not rely on writing. It endures in the stone itself, carrying the traces of voices that once shaped this underground world.